the flow of probability this way is mu2 beta. Now that's a different equation than this, but it's the same way of thinking. In other words, the net probability flow from state 1 to 2 and 2 to 1 is the same. That would give you stationarity. So it gives you that mu2 is equal to mu1 times alpha over beta. Or mu1 is equal to beta over alpha plus beta, doing the algebra. And this is alpha over alpha plus beta. Plug that in here, you'll see that it's a stationary distribution. So here's the point. If I start this Markov chain here in state 1, here's a typical sequence, it's not stationary. I can sort of tell I started in state 1. In fact, I'm in state 1 at time 1. But if I start in state 1 with probability beta over alpha plus beta, if I make x1 a random variable with that distribution, then the process is stationary. Here's another example. Gambling. You go up with probability alpha, and you go down with probability beta. And the probability distribution that works is, what is it? It's in the ratio 1. Is it alpha over beta? Or beta over alpha? Did I work it out? Maybe I didn't. 1 alpha equals mu2 beta. So this is alpha over beta. And then this is alpha over beta squared. And then we better normalize these. 1 plus alpha over beta plus alpha over beta squared. So that's for this first one. So this would be the stationary distribution for the random walk on 3 states, which you move right with probability alpha, you move left with probability beta, and you may stay in the end state when you don't move. By the way, the matrix for here, P, is, let's see, 1 to 1, alpha, alpha bar, beta, beta bar. So for this first example, that's the transition matrix. So once I give you a transition matrix, you can solve for mu. It's the eigenvector associated with the eigenvalue 1, and the Perron-Frobenius theorem says there always exists such, as long as the matrix is stochastic, which means that the entries are non-negative and that the row sums are 1, and all is well. Now let's look at entropy rate. Does it grow linearly? So here's h of xn, sequence of length n, and here's n, 1, 2, etc., n. And let's say you start in state x0, and what's the entropy of x1 and x0? It's something. And then entropy of x0, x1, and x2, it's something greater because there are more random variables involved. And so it's monotonic increasing. But does it look like that? No. Excuse me. Or does it look like this? Does it grow linearly? Notice, if xi or iid, then h of x super n is just n times the entropy of one of them. And that does grow linearly. So is there any Markov dependence we can put in that would somehow make this process more sluggish and cause the entropy not to grow linearly? And the answer is no. It does go up linearly, asymptotically linearly. So, definition 1. Let the entropy of xn over n, the limit as n tends to infinity, equal h. This is by definition, and this should be entropy of the stochastic process. So I'll just put the alphabet in there. The entropy rate of the stochastic process. So if this limit exists, then for any stochastic process for which this limit exists, I can find the limit of the entropy of a block of n symbols divided by n. And I'll call that h of x. Here's another definition. Somebody says, I don't know, that's not my idea of entropy rate. My idea is the innovations. How much entropy is there in the next symbol? I'm reading a book. How random is the next symbol in the text? So we have limit as n tends to infinity of h of xn, the nth symbol given the past, 1 through n minus 1. Now that limit might not exist, but if it does, we'll define this to be h prime of script x. So there are two notions of the entropy rate. So I'm going to show that these two definitions are the same for stationary processes, that h equals h prime. Theorem. H, the entropy rate this way is the entropy rate defined this other way for xi stationary. All right, the way we prove it is 1. All right, proof. H prime exists. I mean, the limit exists, so we can call it H prime. Here's how you prove it. The entropy of Xn given x1 through xn minus 1 is the entropy of the next symbol given the previous n minus 1. Now that's less than or equal to the entropy of this symbol given less information. Information doesn't hurt. So x2 through xn minus 1. Okay? So I've just deleted x1 from the conditioning. The entropy will go up. But now I invoke stationarity. And I say, the joint distribution of all of these is unchanged when I translate every index by, let's say, 1. So, in particular, this functional xn minus 1, this thing that depends on that joint distribution will be unchanged. So, from this we conclude, just from stationarity, no Markovity, that the entropy of the next symbol, given the past, decreases. Decreases. Wait, or is it increasing? Yeah. This entropy. Oh. This isn't what I wanted. Xn. This decreases. Let's see. Yeah. That's this term. It's less than the one before. Great. But this is greater than or equal to 0. Now it's well known that if you have a sequence that's bounded below, in this case by 0, and it's monotonic, then it must have a limit. Therefore, limit exists. Because it's monotonic, decreasing, and bounded below. Great. So we now know that H prime exists. Now we want to show 2. Show H of x, the block thing, equals H prime of x. And from there on, I'll be dropping the prime and just talking about entropy rate. Well, here we use the